Okay, advanced chem students, welcome to our second lesson over neutralization. In this lesson, which is actually pretty short, we're going to discuss salt hydrolysis and how buffers maintain a consistent pH. So, first, salt hydrolysis. So salts are actually formed in a neutralization reaction. We talked about that yesterday. So an acid and a base will react together and form a salt. Solutions of salts, actually though, depending on what the acids and bases are that are mixed, can be either acidic, basic, or neutral, which may seem odd, but that's okay. That's why we're learning this. The base actually contributes the cation of the salt, and the acid contributes the anion of that salt. So in the case of the acid, it's going to lose the hydrogen ion. So this, whoa, we're on the wrong thing. The acid is going to lose the hydrogen ion, so that will lose the hydrogen ion. And then the base is actually going to lose the hydroxide. So it'll lose the hydroxide ion. What will be left is, of course, the cation from the base and then the anion that came from the acid. Sometimes part of the salt hydrolysis actually reacts with water to form hydroxide or hydronium or H+. This is called hydrolysis, and when this happens, it makes the salt behave slightly acidic or basic, and that's what I'm going to show you. So there are a few examples here. The first one is sodium hydroxide and hydrochloric acid. Hopefully you guys know by now, hopefully, that this is a strong base and this is a strong acid, right? So the salt that's actually formed here is NaCl, so that is NaCl. The parent base, now what you had to know was how you made NaCl. Now I've written the reaction here for you, so it's pretty easy to see, but you should be able to look at a salt, or look at, in this case, salt, and see that it is made from NaOH and that it is made from HCl. So a lot of times you're just going to be given a salt and you'll have to be able to determine what they're made from, and we'll do that in a little bit. But this one, the salt is NaCl. The parent base is going to be sodium hydroxide, which is strong, right? That's a strong base. And the parent acid is going to be HCl, and that is going to be a strong, or it is a strong, spelled acid wrong, acid. The pH of this salt, because both of them are strong, they're going to dissociate 100%. The pH of that actual salt that is produced is neutral. And salts of strong bases and strong acids are always neutral. They don't actually react with the water. Here it is written pretty for you. Same thing. But this is really down here the why. Salts of strong acids and strong bases, they kind of cancel each other out. And so there's not a part of the salt that reacts with the water, producing future or additional hydronium or hydroxide ions. So this would be considered a neutral salt, is NaCl. So let's go do another one. So here, the salt that is produced, and it's always going to be on the product side, it's going to be a cation and an anion making a metal and a polyatomic ion, or a metal and a nonmetal. This salt is potassium acetate, so C2H3O2. The parent base here is KOH. Now KOH, as you know, I hope, is a strong base because it's got hydroxide in it. And the parent acid here is actually acetic acid, which is C2H3O2. This is a weak acid. So the pH of this salt will actually be basic. Now, the way that you can figure this out or be able to determine whether it's acidic, basic, or neutral is pretty easy. You can just say the strong one wins amongst the parents. So if a strong base is added to a weak acid, you'll have a basic salt. That's the quick and easy way to determine if it is a basic salt. But the why behind it is a little bit more, there's a little bit more to it than that. So the why is, the way that you prove the why is by taking the weak part of the salt. The weak part of the salt is produced by the acid. So if I go back up to my salt, the weak part of the salt is actually the acetate anion. So what I'm going to take is C2H3O2 minus the weak half or weak part of that salt, and you add water to it and you predict the products. So if I do that and I predict my products, one of the hydrogens is going to go to reform the original acid. So that would be HC2H3O2. And the other product would be, because I removed that hydrogen from the water, hydroxide ions. This would actually be kind of an equilibrium expression here. Correct. This is evidence that it produces, if I have this in solution or in that salt, it actually produces a weak acid and hydroxide ions. That's why it's a basic salt. So if I go forward, show you the prettier version here. The anion, or in this case, the weak part, which came from the acid, reacts with water to produce base, or produce hydroxide ions. This is why it does it, or this is the result of having something that is both strong and weak parent, or having both strong and weak parents. So what you have to be able to do in order to do this, if you're not given the equation, is you'll be given the salts formula, and you have to say, okay, the potassium came from KOH, and the acetate, the second half, came from the weak acid. Well, the strong one will win. That tells you it's a basic salt. So if the question asks you, is this an acidic, basic, or neutral salt? It's a basic salt. If it asks you how to prove that it is a basic salt, you must take the weak part of that salt, in this case from the weak acid, add water to that weak part, and then predict the products. And in this case, it demonstrates that, yeah, giving off hydroxide would make that solution basic. So let's do one more. Here we have ammonia reacting with hydrochloric acid. Why don't you guys try this? I'll write the salt here in H4Cl. That's the salt that's produced. Write and go ahead and fill in what the parent base is, what the parent acid is, and what the pH of that salt is. And I'll come right back to you. And if you guys want to press pause, do that real fast, then come back a minute or two later and hit play. Okay, so the parent base here, if you look at ammonium chloride, ammonium, it would be ammonia. And the parent acid, since it's a chloride ion given off as the anion, it would be HCl. So the pH of the salt, acidic, basic, or neutral, this is strong, and this is the parent that is weak. So being that that's the case, this is going to be an acidic salt. Yeah. The why, the way that you prove the why, and I kind of hope that you guys did this, but if not, that's fine. Take the weak part, which in this case is the ammonium. So I'm going to take NH4 plus, and I'm going to add water to it and predict my products. My products will be H3O plus. No, that's not. Yeah, that's right. I'm losing my mind. H3O plus and NH3 is the other product. So that means that if you're giving this off in solution, it will actually be acidic. So here's the prettier version, but the same. The cation is going to react with that water, the weak part. Always take the weak part, add water, predict your products. That's how you prove whether or not a salt is acidic, basic, or neutral. You can't leave that out. You guys will definitely be asked to do that at both this level as well as next year in AP Chem. Okay. Salts of weak acids and weak bases, they're both weak. So it depends. One of them may be slightly stronger than the other. And you would have to look at the Ka value or the Kb values to determine which is the weaker part. You would take that weaker part and add water and predict whether it was acidic, basic, or neutral. But once again, you can kind of just say to yourself, now, you can't write this down as the reason. You have to take the weak part and add water to prove the reason. But if you just have to identify it quickly, which is most of what you'll do, the stronger one always wins. So if the higher Ka value, if the Ka value was higher, it would be an acidic salt. If the Kb were higher, it would be a basic salt. So let's go through and do this. I'll do a little bit, maybe the first one with you, but I want you guys to try to do this on your own. So here's a series of salts, and you need to figure out what the parents are, the parent acid and the parent base, and then figure out just what type of salt it is. If it's going to be an acidic or basic salt, then you write kind of underneath here, or wherever on your paper, write the evidence for it, which means take the weak part and add water to it. So in order to, let's just do this first one here, and I'll let you guys do the rest. So sodium nitrate, the parent base is sodium hydroxide. And the parent acid would be nitric acid, HNO3. This type of salt, because they are both strong, would be a neutral salt. So I wouldn't have anything to do there. I wouldn't have to prove anything to it. For this one right here, actually, you know what? I'm not going to go there. I want you guys to give it a shot. Go give it a shot. Yeah. So do me a favor, and if you're doing this right now, go ahead and press pause. Finish this up, and then come back to it in a little bit. Hurry up. Press pause. Okay, so let's assume you press pause. And now you're back, and you've got a filled out chart, and we're discussing this. So this one right here, the second one, is ammonium nitrate. The parents of ammonium nitrate are going to be ammonia. That's going to be the base, NH3. And the parent acid is going to be nitric acid. Now, nitric acid is strong, so it's going to win. So this is going to be an acidic salt. Okay? I have to prove that it's an acidic salt, though. So acidic basic, you need to prove. So I'm going to take the weak part of the salt, which is the ammonium, and I'm going to add to it water, and we had this already earlier. I end up getting NH3, and the water gains the hydrogen, becoming hydronium, and this is evidence that it is an acidic salt. Let's go do the next one. The next one is a little bit more difficult. Yeah. Actually, you know what? Let's skip and do the last one. Get a little creative here. We'll do the last one. So this one, the parent base is sodium hydroxide, which is a strong base. And the parent acid is going to be H2CO3, carbonic acid, which is a weak acid. And so I've got a strong base and a weak acid. So that means the strong one's going to win. So in quick identification only, I could say, okay, this is a basic salt. But then I have to prove that it's a basic salt by, once again, taking the weak part of the salt, which in this case is the acidic part, and adding water to it. So here I would say this is a basic salt. And I'm going to take the weak part of the salt, which is the HCO3 minus, and I'm going to add to it water. One of the hydrogens will transfer and reform the parent carbonic acid, and you'll be left with the water losing a hydrogen, hydroxide ions. There is the evidence that it is a basic salt. Let's go do that last one. I've got some eraser issues here. Let's see if this that doesn't work better. Okay. Always a learning curve with Toilet. Okay, so on this last one here, let's see if this is nah. Ooh. Sorry guys. Trying to figure out a way to make this go a little faster, and it's not doing it. Okay, so for the ammonium acetate, hopefully you put that the parents were both weak. So yeah, both of these guys are weak. If they're both weak, then we're going to have to look at their Ka and Kb values. Now, I didn't give them to you here, but I would give them to you in a quiz or an exam or something like that. So here, I have the parent base is ammonia, and the parent acid is acetic acid, HC2H3O2. So this one I need to figure out what type of salt it is. In order to do that, I'm going to need to know what the Kb is for the ammonia and what the Ka is for the acetic acid. So the Kb is 1.8 times 10 to the negative 5, and the Ka is 1.8 times 10 to the negative 5. Now we got lucky here. The Ka and Kb are the same. If they're the same value, then it's just like having weak, but they're both as weak as each other. So this would, in fact, be a neutral salt. Now, had it been different, had one of them been larger than the other, it would be a basic or an acidic salt, and you'd have to predict it the same way. So I know that is, here's the prettier version of that. I know it's a little complex, a little difficult, but we'll do some more practice of this and get you guys through it. So where this kind of comes into play, yeah, if you added salts to water, you would need to know whether they were acidic, basic, or neutral. And a lot of cleaning products are salt-based solutions. Baking soda is a good example. Baking soda is sodium bicarbonate, and so it's actually a basic salt, and it can be used to clean things as well. But buffers are things that use parts of salts or parts of acids and bases to actually resist shifts in pH. So to maintain the neutrality or basicity or acidity of some solutions. So buffers consist of two things. They consist of a weak acid and one of its salts, or the weak part of the salt. So, or if you like, its conjugate base or its conjugate acid as well. The buffer capacity is the maximum amount of acid or base that can absorb, not allowing any large changes in pH. Now, you guys aren't going to have to calculate any buffer capacities or do any calculations with buffer components or problems. We will do that in AP Chem, but you do need to identify buffer systems and figure out whether it will absorb or release hydrogen or hydroxide ions. So listed below here are some of the common buffer systems. The acetic acid acetate or ammonium are super common. Those are the ones we usually use. And then the other two, carbonic acid and the dihydrogen phosphate, are also good buffer systems. Those show up in your blood to maintain a consistent pH. When strong acid or base reacts with a buffer, one part of the buffer changes into the other one. And this is much easier to see when I do some reactions with you. But what happens if you add H plus to acetate? What do you get? You get the other half of the buffer system. Same thing if you added hydroxide to ammonium, you would produce ammonia. And by doing that, what it does is absorbs those hydrogen or hydroxide ions that you're adding in acidic or basic solution, and it maintains neutrality. So if this is my buffer system here, and I add an acid, a generic acid is just written as adding H plus. So if I add H plus, it's going to add to one of those two substances to produce the other. So in this case, it would actually add to, the bicarbonate, HCO3 minus, producing H2CO3. If I added a base, hydroxide ion, it would actually add to H2CO3, and it would produce the bicarbonate, HCO3 minus, and water. So if you notice, I've got acid on one side of the equation and base being added on the other side of the equation. And as my products are concerned, I get neutral substances. So what this does is, if you have both of these things present, say in equal concentrations, it depends, but in certain concentrations, it will absorb hydrogen ions and it will absorb hydroxide ions and produce the other half of the buffer system. The same thing happens with the ammonium buffer system. If you add acid to it, it will combine with the NH3 and it will produce the other side, which is NH4+. Having absorbed the hydrogen ion, it will maintain neutrality. If I added hydroxide ion and it combined with the NH4+, it would actually produce NH3 and water. Again, maintaining neutrality of the cell, or of the solution. Shouldn't say cell. In your blood, that's absolutely true. But yes, this is how this works. And so buffers are a huge component of things. They're very difficult as far as the calculations are concerned, but just understanding here how they absorb hydrogen or hydroxide ions and produce halves of buffer systems is what we want you to take away from this. So here are the two buffer systems that are in the blood. They're listed down here. Blood needs to maintain a pH slightly above 7. And so in order to do that, the bicarbonate and dihydrogen phosphate buffer systems are present, both. So it can either absorb or release hydrogen or hydroxide ions to kind of maintain that neutrality. So this is something that you see quite a bit. We do several of these in AP chemistry, where we do actual calculations. We'll calculate and determine the buffer system that is present in lemonade, which actually maintains the neutrality of or actually maintains the acidity, I should say, of the lemonade, depending on what municipality you're in. So if you use different water source for your water, your lemonade still tastes the same, or at least they can maintain the acidity of it. Anyway, so that'll be for next year. But that concludes what we're going to talk about for this for buffers and salt hydrolysis. I'll see you guys in the next unit. I'll see you in the next unit.